Welcome to our deep dive. We're going to be tackling math today.
But not your typical numbers and equations kind of math.
Right, more like, how do we even do math, you know?
Like what's going on in our brains when we think mathematically?
Yeah, exactly. And for this deep dive, we've got Keith Devlin's book, The Math Gene.
Oh, a fascinating
It
read.
really makes you think differently about math.
He actually calls math the science of patterns.
Okay, I like that, the science of patterns, so it's not just about, like, crunching numbers.
No, it's about recognizing those abstract relationships and logic behind everything.
So, like, is there a pattern to how the universe works, or
Well, it gives this cool example about wallpaper patterns.
wallpaper patterns?
Yeah, apparently there's only a limited number of ways those patterns can repeat infinitely.
Huh. Who knew there was math behind interior design?
Right. And then he even talks about how math helps us see things we couldn't otherwise.
Like, what do you mean?
Like animal patterns, you know how zebras have stripes and leopards have spots?
Oh, yeah.
Well, those patterns can actually be linked to simple mathematical equations.
So math is literally hidden in plain sight all around us.
Exactly. It's governing so much of our world, even if we don't realize it.
Okay, so that's patterns. But what about this whole math gene idea? Is Devlin saying we're all, like, born mathematicians whether we like it or not?
Well, his big idea is that the same part of our brain that handles language is also what lets us do math.
So there's, like, a connection between how we talk and how we think about numbers.
Right. He believes there's this innate number sense. We're born with something present even in babies.
Babies, really?
There are studies where babies as young as 4 days old react to changes in the number of objects they see.
Wait, so even before we can talk, we have this sense of number.
It seems that way. It's just something fundamental is wired into our brains.
Wow, that's incredible. And he says it's not just humans, right?
Right. He talks about research on chimps showing they can understand fractions and do basic addition.
Chimps doing fractions. Okay, now I'm impressed.
Of course, their abilities are limited compared to humans, but it suggests this number sense might have deep evolutionary roots.
So if chimps can grasp basic math, what makes us so different? What takes us to that next level?
That's exactly what Devlin argues. He dives into the evolution of the human brain, pointing out that it's incredibly energy intensive.
Okay, so our big brains had to earn their keep, evolutionarily speaking.
For something that costly to develop, there had to be a massive survival advantage.
So what was it about our brains that gave our ancestors an edge?
Devlin connects it to a concept called offline thinking. It's the ability to run simulations in our minds.
Like a mental time machine.
Exactly, playing out different scenarios and their consequences without needing a real-world prompt.
That's got to be useful for, like, planning and strategizing.
Incredibly useful, and Devlin believes this offline thinking ability is deeply linked to both language and math.
So language helps us think ahead,
Yeah.
and that helps us with math too.
It allowed our ancestors to plan, strategize, and adapt to changing environments in a way that no other species could.
Okay, I'm starting to see those connections between language, thought, and math. But how does this offline thinking actually work in our brains?
That's where things get even more interesting. Devlin talks about the concept of a mental number line.
A mental number line.
Yeah, the idea that we visualize numbers spatially. Have you ever noticed how it's easier to compare small numbers quickly than larger ones?
You know, I never really thought about it that way. But yeah, I guess so.
That's because they feel further apart on that imaginary line in our minds.
So our brains aren't just processing numbers abstractly, we're picturing them.
Exactly, and this mental number line idea is just one piece of the puzzle. Devlin mentions cases of people who can read numbers but not words, and vice versa.
Really?
Yeah, that suggests how our brains handle these different symbols might be quite distinct.
Huh. It makes you wonder how much of our mathematical ability is about how our brains are physically wired versus what we learn.
And that leads us to another point Devlin makes, that our brains might not be ideally suited for the kind of precise numerical manipulation we often do in math.
Like, what do you mean?
Think about multiplication tables. Why are those so hard to learn?
Don't remind me. I still have nightmares about those.
Well, Devlin suggests it's because we're using the wrong mental tool for the job.
Like trying to fit a square peg in a round hole.
Exactly. We're forcing our brains to do something they weren't designed for.
So maybe there's a better way to approach math education.
He even brings up how different number systems, like in Chinese, can actually make learning math easier because they map more intuitively onto our mental number line.
Wow. So the way we talk about numbers can actually impact how well we understand them.
It seems that way language really seems to be at the heart of it all.
This is blowing my mind. I'm starting to see math in a whole new light.
Devlin is building a case that language and math are deeply connected, maybe even sharing a common origin in our evolutionary history.
So it's not just that language helps us communicate mathematical ideas, it's that the structures of language might actually shape how we think mathematically.
Right, and we'll dive into more of those connections in the next part of our deep dive.
Definitely stay tuned because we've got a lot more to unpack.
There's so much more to explore in the fascinating world of the math gene. Welcome back to our deep dive into the math gene.
So before the break, we were talking about how language might actually shape the way we think about math.
Right, and that leads us to another really intriguing part of Devlin's book, how mathematicians actually think.
Okay, because I have to admit, when I picture a mathematician, I think of someone like, scribbling equations on a chalkboard, all logic and precision.
It's a common image, but Devlin paints a much more nuanced picture.
Oh, really? So it's not all just like cold, hard logic.
Well, while logical proof is the gold standard in math, the process of getting there is often much more messy.
Messy, how so?
He points out that it often involves intuition experimentation, even making educated guesses.
Wait, so mathematicians make guesses? I thought it was all about certainty, like finding that one right answer.
And that's what's so refreshing about Devlin's perspective. He emphasizes that there isn't always a single right answer in math.
Huh, so it's not like solving for X in algebra.
Not necessarily. There can be more elegant or less elegant approaches, just like in creative fields.
So it's more about the journey than the destination?
In a way, yes, it's about embracing the challenge, the uncertainty, and the thrill of discovery.
Okay, I like that it makes math sound a lot more adventurous.
He uses this great analogy of exploring a mountainous landscape.
Oh, I like analogies.
Sometimes you have to wander through valleys, get lost in the woods before you find your way to the peak.
That's a great analogy.
Mhm.
I can definitely relate to that feeling of being lost and then suddenly having that aha moment.
And those aha moments are key in math, too.
So it's not just about following a set of rules, it's about having those flashes of insight.
Exactly. And this brings us back to Devlin's core argument, the connection between math and language.
Right, because we were talking about how language might be the foundation for those higher level math skills.
Exactly. Devlin argues that while mathematicians don't literally think in language, our capacity for language for symbolic thought is what makes that higher level mathematical reasoning possible.
So it's like language provides the building blocks, the scaffolding, for constructing those abstract concepts.
Exactly. And that's where the idea of abstraction becomes really important.
Oh yeah, we were talking about different levels of abstraction earlier, like how a dog might understand food, but not the abstract concept of nutrition.
Perfect example. Devlin argues that mathematical thinking happens on a really high level of abstraction.
Okay, higher than nutrition.
We're dealing with objects and relationships that don't have a direct physical counterpart in the real world.
So it's like creating a whole new world inside our minds.
A world of pure concepts and logical connections, a world built with the tools of language.
That's pretty mind-blowing. I have to admit I'm having a little trouble wrapping my head around this level of abstraction.
Well, Devlin uses this example of group theory to try and illustrate this.
Group theory. Sounds a little intimidating.
I know, but he does a great job of breaking it down. He starts with something familiar, like the symmetry of a circle.
Okay, a circle. I can handle that.
You know how a circle looks the same no matter how you rotate it?
Right, it's perfectly symmetrical.
Well, that rotational symmetry can be described mathematically using transformations,
Transformations.
like rotating it, flipping it, things like that. But then Devlin takes it a step further. He shows how we can abstract away from the specific example of a circle and focus on the underlying patterns of those transformations.
So we're going from something concrete and visual like a circle to something more conceptual and abstract.
Exactly, and that's where group theory comes in. It's a
Mhm.
way of studying those abstract patterns of symmetry and applying them to all sorts of things that seem totally different at first glance.
Wow, so we can use the same mathematical concepts to understand things like the shape of a galaxy or the structure of a molecule.
It's all connected by these underlying patterns, and that's the beauty of math. It allows us to see those connections between seemingly unrelated things.
Okay, I think I'm starting to see the power of this, but my brain is definitely feeling the stretch.
It's a good stretch, though, right?
Yeah, definitely makes you think.
And that's what Devlin wants. He emphasizes that even the most complex math is ultimately about solving problems, understanding relationships, and finding those elegant solutions. It's not just about crunching numbers.
So it's about seeing the bigger picture.
Exactly. And he stresses that anyone can develop this kind of mathematical thinking. It's not about being a genius.
It's about finding that spark of interest, that sense of purpose, that drives us to want to understand.
Precisely. But let's address something really important here, the fact that so many people struggle with math.
Yeah, that's a big one if we all have this math gene. Why is it such a challenge for so many of us?
And Devlin dedicates a big chunk of his book to exploring this very issue.
Does he have any answers?
Well, he acknowledges that the way math is often taught doesn't do us any favors.
Yeah.
It fails to tap into that innate capacity for math thinking that we've been discussing.
Yeah, I can definitely relate to that. I remember feeling totally lost in math class. Like I was just going through the motions without really understanding what I was doing.
And that's exactly what Devlin criticizes. He argues that when math is presented as just a bunch of rules to be memorized, it loses its connection to real-world problem solving and the joy of discovery.
It becomes this abstract, disconnected subject that feels irrelevant to our lives.
And that's when people start to tune out. They lose that natural curiosity and sense of wonder that we all have as children.
So it's not about the math itself being inherently difficult. It's about how it's taught.
To a large extent, yes. He stresses the importance of making math relevant to students' lives, connecting it to their interests and experiences.
Like that example we talked about earlier of the Brazilian street vendors.
Exactly. They're brilliant at doing math in the context of their work, but struggle with formal math problems in a classroom.
It highlights how crucial motivation and meaning are for learning when we see a purpose in what we're learning, when we're engaged and curious. Our brains are much more likely to make those connections.
And retain that knowledge. It's not about making math easier, it's about making it matter.
About showing people why it's relevant to their lives.
Precisely, Devlin argues that we need to shift our focus from rote memorization to fostering a deeper understanding of math concepts.
So less drilling multiplication tables and more problem solving and critical thinking.
And he believes that this approach can unlock the potential for math in everyone, regardless of their past experiences.
That's really encouraging to hear. But practically speaking, how do we make this shift happen? What can teachers, parents, even learners themselves do to cultivate this kind of math thinking?
Devlin offers some really practical advice here. He emphasizes hands-on activities, problem-solving challenges, and exploring math in real-world contexts.
So it's about approaching math as a creative endeavor, a process of exploration and discovery.
Exactly. He believes that when we tap into that sense of playfulness and curiosity, we're engaging those deeper cognitive processes that make math click.
It's like we're reawakening that math gene that might have been dormant for a while.
And this brings us to another fascinating aspect of Devlin's book, his exploration of the role of beauty in math.
Okay, now that's not something I typically associate with numbers and equations when I think of beauty. I think of art, music, nature, not calculus.
I know it seems counterintuitive, but Devlin argues that there's a deep aesthetic appreciation that comes with understanding math concepts.
Really? So mathematicians are like art critics, but for numbers.
He compares it to the beauty we find in a perfectly crafted piece of music or a stunning work of art. There's a sense of elegance, harmony, and awe that can be just as powerful in mathematics.
Okay, I'm intrigued, but I need some convincing. Give me an example of this mathematical beauty you're talking about.
He uses the example of Euclid's proof of the infinitude of prime numbers.
Prime numbers, refresh my memory.
Those are the numbers that can only be divided by one and themselves, right?
Right.
And Euclid's proof shows that there are infinitely many of them. It's a classic proof that's been admired for centuries for its elegance and simplicity.
So what makes it so beautiful?
Devlin points out that this proof is considered beautiful not just because it's logically sound, but because it's so concise, elegant, and surprising in its approach. It's like a perfectly formed puzzle piece, fitting into place in a way that feels both inevitable and awe-inspiring.
So it's like finding that perfect solution, that aha moment that reveals a deeper truth in a way that's both profound and aesthetically pleasing.
Precisely. And Devlin argues that this appreciation for beauty in math is something we can cultivate just like our appreciation for beauty in art or music.
That's a powerful idea. It's
Yeah.
like he's opening up a whole new dimension of math, one that goes beyond just getting the right answer to finding those moments of genuine awe and wonder.
And those moments of awe and wonder are what keep us coming back for more. They're what fuel our curiosity and drive us to explore the world around us with a sense of excitement and possibility.
Welcome back to our deep dive into the math gene. It feels like we've been on this incredible journey exploring all these fascinating ideas about how our brains work.
Yeah, we've covered a lot of ground from that whole science of patterns thing to the surprising connection between math and gossip.
And that idea that math is more about understanding than just crunching numbers.
Right, and that it might be more widespread than we think, even if traditional education doesn't always bring it out.
We've even touched on that fascinating concept of beauty in mathematics, which I have to admit is still kind of blowing my mind.
It is mind-bending, isn't it? But before we wrap up our deep dive, I want to circle back to something you mentioned earlier, that challenge of making math more accessible and engaging for everyone.
Oh, yeah, because Devlin definitely has a lot of practical advice on how we can make that shift, moving away from rote memorization and focusing on deeper understanding.
And one of his key points is that we need to change our mindset about what math is and who can do it.
Yeah, like challenging that idea that it's only for geniuses or people who are naturally good at numbers.
Right. He argues that anyone can develop those mathematical thinking skills. It's just a matter of finding the right approach, the right spark.
And he really emphasizes the importance of starting early, nurturing that sense of curiosity and playfulness around math in young children. So like creating a positive and supportive environment where kids can explore math without being afraid to make mistakes.
Exactly, where it's okay to experiment and play around and see what happens.
It makes you wonder how different our relationship with math might be if we'd all had those kinds of experiences early on.
And Devlin stresses that it's never too late to develop those math thinking skills, even for adults who might have had negative experiences with math in the past.
So there's hope for me yet.
Absolutely. He argues that we all have this innate capacity for math. It's just a matter of finding that spark, that entry point that ignites our curiosity and makes us want to explore further.
I have to say the math gene definitely sparked my curiosity. It's given me a whole new perspective on math and its importance, not just as a subject we learn in school, but as this fundamental way of thinking about the world.
That's fantastic to hear, and I think that's one of Devlin's greatest achievements with this book. He's not just trying to teach us about math, he's trying to make us think differently about it and its role in our lives.
And he's done a brilliant job of that. But before we sign off, I'm curious what stood out to you the most in all of this? What were your big aha moments from the math gene?
For me, it was realizing that math is so much more than just calculations and formulas. It's about seeing patterns, making connections, understanding the underlying structure of the world around us. And that's something that everyone can appreciate regardless of their background.
I totally agree. And what really resonated with me was the idea that math is a creative endeavor. It's
Oh,
about
yeah.
finding those elegant solutions, those moments of insight that reveal a deeper truth. It's not just about logic. It's about intuition and imagination as well.
Yes, and that sense of creativity and discovery is what makes math so exciting and rewarding. It's not about finding the one right answer, it's about exploring the infinite possibilities.
Well said. So as we wrap up this deep dive, what final thought would you leave our listeners with? What's one thing they can take away from the math gene and apply to their own lives?
I would encourage everyone to embrace the challenge of math, to see it not as a hurdle to overcome, but as an opportunity to explore the incredible power of their own minds. Devlin's book reminds us that we all have this innate capacity for mathematical thinking, and that when we tap into that potential, we unlock a world of possibilities.
Beautifully put. So to our listeners, I say this, go forth and explore the world of math with curiosity and confidence. You might be surprised by what you discover, and until next time, keep diving deep.